Welcome to Brain Vision.
We have a coal-fired steam power plant that produces 175 megawatts, or 175,000 kilowatts. The high pressure side is at 7 megapascals, or 7,000 kilopascals, and the low pressure side is at 15 kilopascals. The temperature going into the turbine is 550 degrees C. And we're told the heating value for the coal, so basically the energy released when it's burned, is 29,300 kilojoules per kilogram. We have the efficiency of the turbine is 96%. We're told that the efficiency of the boiler is actually, we have an efficiency of the boiler of 85%. So that's basically saying that we only get 85% of the heat that out of what we burn, because obviously some of the other is going to be wasted and go into heating other things or being lost, and not going into the steam or to the water here to boil it. So we get 85% of the energy out of the coal. We can figure out, let's see here, we know pressure and temperature at 3, so we can get the enthalpy and the entropy at 3. We know, let's see here, we can figure out the, what do we have then? This is actually an ideal case. I didn't draw this correctly. So this is 4 should actually be directly below 1. So, and 2 should be directly above. 4 should be directly below 3. And so let's fix this in here and fill this all in. And then 2 should be directly above 1. So we have 4 here, and we have 2 here. So yeah, that's well, we can do that because again we're told, we're given the efficiencies and we don't really need to figure out. So this is actually let's see here, 4 prime, right? So let's see here. We can get the quantities at 4, or these are kind of, again, I'm not really making a distinction here because we have this efficiency that we're going to add in later because we're given enough information. So we can figure out because we can figure out the heat transfer here and the heat transfer here. We can figure out the thermal efficiency of this cycle. It's let's see here. We have then, it's kind of a different way of going about it than I have in previous problems. But again, it's good to kind of see different things, different ways of approaching these problems. So again, we're going to take, these are all, I should probably, to make things clear here, say this is 4 prime, 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 and yeah, that should be it. So again, we can figure out 4 prime because we know S at 4 from S at 3, and we know the pressure at 4. So we can get the quality factor and the enthalpy there, and this should be a prime also. And so we can also get the enthalpy at 1, and the specific volume at 1 because it's on the saturation, it's saturated liquid. We can get the work that goes into the pump as usual, and then the specific enthalpy at 2, which is just this plus this from a conservation, from energy balance on the pump. Now the heat going in is enthalpy here minus enthalpy here, So that's 3,299 kilojoules per kilogram. The heat going out from, in the ideal case, is 2,026.8 kilojoules per kilogram. So then the thermal efficiency, I should write this in here, is 1 minus, let's see here, Q, what's Q out prime minus Q in. All right, so that gives us 38.56%. Now the total efficiency we can get by taking the thermal efficiency of the cycle, multiplying it by the efficiency of the turbine, and then multiplying that by the efficiency of the boiler. So this is kind of giving us an efficiency totally of what energy we would have in the coal, to an efficiency of how much we're getting out as work from the energy that we got from burning the coal. So again, not all of the energy from burning the coal is going into the boiler, and not all of the energy coming from, in reality, we have a line from here somewhere down to here to 4. So in reality, we don't have, we have some losses there, so we tack that in there too. So these losses are cumulative, so they're multiplicative. And in the end, we get 31.5% efficiency for this total cycle as we go, as we look at the efficiency from from going from the energy in the coal to the workout that we get from the turbine. And now we can figure out the rate of heat transfer into the into our system here, and that is the rate of work out, or the power. What did I write that there? Well, why did I write this? I think I wrote in, and I should have wrote net. So this should be net as usual. So just knowing the efficiency, now we can get the heat transfer in here. Divide is the the power in, which we were told, right? So we're told what that is, and we know this efficiency, so we know the rate of heat transfer coming in from the coal, from here, from the coal, is about 556 megawatts. Now, we're told that we were asked to figure out what the kind of the flow rate or the rate of coal that is being consumed. And so we can take the heating, we can take this and divide it by the heating value. Okay, so this will give us the rate essentially the mass flow rate of coal. Obviously, it's not really a flow of coal, although you could think about it as being on a kind of a conveyor belt or something. Now, so what we wind up with getting then is we wind up needing to have about very close to 19 kilograms per second of coal kind of coming through here, which then if you convert it, into a real power plant, they're talking about 68.3 tons of coal per hour. So that's a metric ton of coal per hour is being burned to produce this 175 megawatts.